Hello everyone, my name is Roger Fari and I would like to welcome you to another video. In this short video, we are going to discuss another data transformation technique called log transformation. This technique is a very specific technique. The past two videos, specifically attribute construction and feature extraction, we saw a sort of like a concept of data transformation that we could do in different ways and using different techniques. But log transformation is just one technique that is applied in a very specific situation. So what are those situations? Whenever in your data there is a natural exponential growth or decay, meaning the difference of value between your data objects, it grows, or there is a very big difference between them if you sorted them, and then using log transformation might be able to help you by keeping the relative differences between the data object while making sure that the very large value do not consume your visualization or distance spaces. All right, I think we can learn this best if we look at an example. All right, so let's look at an example here together. So here we've got the 2020 world GDP. So on the x-axis we've got all of the countries, right? And we've got actually more countries than have been written here, right? So this is just it's a part of those countries that have been written here, and the reason for that is we didn't just have much space for including every country in the x-axis, but all of the countries are included in the visual. And on the bottom you can see the box plot that shows the sort of like the differences and the summary of this attribute, right? So we can see that there is a exponential growth, right? There is exponential growth. We've got the median is really close to zero, and then we've got less than 0.1 most of the population, and then there are some population that are way above those larger part of the population, and then there are two that they are just way higher than the rest of the population, right? So that's a case of exponential growth, right? So when we do see such cases, you can see that this visual space and also this visual space are being consumed just because there are these two very big values in our data, right? Not just these two, that's just the way this data is, just like the natural growth of this data. So if we were to replace the value, the original value, with the log transform value, which basically means you calculate the logarithms of the log of each of the value and input them instead, then you will get this other visualization that we can see actual type of a linear relationship here. We can see that we see that there is a continuous growth, and then we also see that we have a much normal looking box plot, right? So even though these are not the original values, but for the purpose of being able to visualize the country and seeing them in a line, and also being able to use other algorithmic ways that by such differences that those differences can disrupt the working of the algorithm, we might decide to go with log transformation. Let's see an example here. So we have the mean body mass of species and also the mean brain mass of species, right? You do see that each of these points are one species. Humans are one of these points as well, right? We do see that the most of the populations are here, but like there are some that have larger values of the brain and some that have larger value body mass, and because of that we cannot use the scatter plot as a way to show the relationship between these two attributes, right? And it's because these larger values are consuming the space of visualization. Whenever such thing happens, one of the ways we can go about this is to use log transformation, right? Once we do log transformation, we actually can see that there is a linear relationship between the mean body mass and mean brain mass, which basically means that if you have a larger body, you're probably going to have a larger brain. Another important usage of log transformation is when you have such attributes that have exponential growth or decay for clustering algorithms, or any algorithm that uses this distance between your data objects. Just because there are some data objects in your data that have such higher value, those higher value are going to be consuming the space of the distance, and it's going to lead to possible biases in your result. So like I said, this was a short video, but if we were to discuss if log transformation is data massaging or not, we do know that it's a data transformation, log transformation. What is it? For instance, in this case, we were sort of like visualizing this, but only after doing the log transformation, the relationship started showing itself. In case of clustering algorithms, if we actually have an attribute that has an exponential growth, it may actually result to your clusters to be a little bit biased, just because one of these attributes or one of these data objects are going to dominate the space of the space of the distance between the data objects, right? So in some cases, you might consider this as an effective tool or as a necessity tool, but because this is a very just simple tool at the same time, most of the time, if you actually don't do it, you're not going to be able to get what you want done, such as showing a relationship between two attributes that have exponential growth or decay. Or if you didn't do this, you would have you would have biased outputs, for instance, clustering or KNN outputs. Because of that, I do think, like I said, between the difference between data transformation and massaging is not black and white, but I would put log transformation as only data transformation and not data massaging. All right, until the next video.